Welcome to the deep dive. I'm genuinely thrilled today because we're taking this document titled Summer 2025 Potential Questions, Final Exam,
Hmm.
and turning it into, well, a journey.
Exactly.
This isn't really about memorizing for a text. It's about equipping you with a solid, intuitive feel for how our planet works, its resources, and, how we interact with it all. Think of these questions more like doorways to some pretty surprising insights. Essential stuff, really.
Absolutely. Our goal here is to unpack these key ideas right from the ground up. We'll start small, like with the basic units of energy, and scale all the way up to, global resource management and how that impacts society.
Right.
And what's fascinating is how it all weaves together physics, chemistry, geology, even sociology. It's all connected.
And hopefully along the way, you'll have some real aha moments. Our aim is clarity, feeling informed without getting totally overwhelmed.
Because understanding these systems, these connections, it's just crucial for tackling modern challenges.
Yeah.
Things like energy supply, sustainable development. It all ties back.
Okay, let's dive in then. So our document starts us off with something fundamental. The universal language of energy. When we talk energy, there's like one main unit, right? The standard.
That's right. It's the joule, spelled Joule, and abbreviated as J. That's the standard SI unit for energy. Think of it as the universal currency for energy.
The baseline.
The baseline, exactly. It measures energy transferred or work done.
But like you said, currency. We use different units day to day, like on food labels.
Good example. For food energy, we typically use the calorie. And the one you see on nutrition labels, often with a capital C, is actually a kilocalorie. One of those is roughly 4,184 joules.
Wow.
Okay, it's just a more convenient number for talking about, how much energy is in your lunch.
Makes sense. And definitely not joules on my electricity bill. That's something else entirely.
Definitely not. Power companies use the kilowatt hour, kilowatt-hour. It avoids these massive numbers, but it's still based on joules. 1 kilowatt hour equals 3.6 million joules.
3.6 million, okay.
Yeah, it's a huge bundle of energy packaged for convenience.
So joule is the base. Calorie for food, kilowatt for electricity bills.
Oh.
Those measure the amount of energy. But what about the rate? How fast we use it?
Ah, that's a crucial distinction. Energy amount versus energy rate. For the rate how quickly energy is used or produced, we use the watt, W.
Right.
A watt is simply defined as 1 joule per second, JSS. It tells you the speed of energy flow.
Like the classic light bulb example.
Exactly. A 60-watt bulb uses 60 joules of energy every single second it's on. So watts help you compare how quickly different devices consume energy.
Got it. So joules are the base currency, calories and kilowatt for like specific denominations for certain transactions, and watts tell you how fast you're spending that energy currency.
That's a perfect analogy. It's all interconnected, just scaled for different purposes.
Okay, that energy foundation is clear. Now let's pivot to how Earth's atmosphere manages energy. The document calls it Earth's atmospheric blanket. What's actually in this blanket?
Right. The main atmospheric composition is dominated by just a few gases. Nitrogen and Euro makes up about 78%.
The vast majority.
Yep. Then comes oxygen, O, at around 21%. After that, argon, R, is almost 1%, about 0.9%.
Okay, so in euro, RR. That's 99.9% right there. What about the rest, the famous ones?
Well, the next biggest player, percentage-wise, is carbon dioxide, QO Euro, but it's only about 0.04%.
0.04%. It always strikes me how tiny that number is, given its massive role in climate discussions.
It really is tiny, but incredibly potent. And then you have even smaller amounts of trace gases like methane, CH, nitrous oxide, NEO, and crucially, water vapor, HO, which varies a lot by location and altitude.
So why is that tiny 0.04% of key euro and those other trace gases so important? How do they behave differently from nitrogen or oxygen when it comes to heat?
It all comes down to their molecular structure and how they interact with long-wave radiation, which is essentially heat radiation or infrared.
Okay.
Nitrogen, oxygen, and argon, the big three, have relatively simple symmetrical molecules. They're largely transparent to the infrared radiation Earth emits. It just passes right through them out into space. They don't really absorb or re-emit it.
Yeah, they let the heat escape.
Pretty much. But the greenhouse gases, oro, methane, nitrous oxide, water vapor, have more complex asymmetrical structures. These structures allow them to vibrate at specific frequencies that match the energy of infrared radiation.
Ah, so they can actually catch that outgoing heat.
Exactly. They absorb it, and then, crucially, they re-emit it. But they re-emit it in all directions, including back down towards Earth's surface. That's the key mechanism.
So it's not just absorbing, it's the re-emitting back down
Yeah.
that traps the warmth.
Precisely. Think of the atmosphere like a layered coat. Nitrogen and oxygen are the bulky, breathable outer layers.
Okay.
But co-oro and the other trace greenhouse gases are like a thin but incredibly effective inner lining. Even a tiny amount of that lining makes a huge difference in trapping your body heat. For Earth, it traps the outgoing infrared radiation. That seemingly small percentage is vital for keeping the planet warm enough for life.
Okay, I like that code analogy. So if that's the composition, let's dig into the mechanism itself, the natural greenhouse effect and its link to climate. How does this heat trapping really work day to day?
So the mechanism of heat trapping starts with the sun. The sun emits energy primarily as shortwave radiation visible light, UV light.
Right.
This shortwave energy passes relatively easily through the atmosphere and gets absorbed by Earth's surface, the land, and oceans, warming them up.
Makes sense. The ground gets warm on a sunny day.
Exactly. Then, the warmed Earth's surface radiates this absorbed energy back outwards, but now as long-wave radiation or infrared heat.
Okay, so the energy changes form, shortwave in, long wave out.
Precisely. And this is where those greenhouse gases, that inner lining we talked about, come into play again.
They intercept that outgoing long-wave radiation.
They do. Gases like carbon dioxide, COC, methane, CH, nitrous oxide, NUO, and water vapor, HO, absorb chunks of this outgoing infrared energy. And as we said, they then re-emit it in all directions. A significant portion gets sent back down towards the surface.
Warming the planet further, like the glass in a literal greenhouse.
That's the classic analogy, yes. It traps some of the heat that would otherwise escape directly to space.
And what determines how strong this effect is? How warm the coat keeps us?
The primary determinant is the concentration of these specific greenhouse gases in the atmosphere. More greenhouse gas molecules mean more absorption and re-emission of that outgoing infrared radiation back towards the surface.
So a thicker inner lining means more warmth trapped.
Exactly.
And the document mentions a historical correlation with temperature. What does the science, like ice cores, tell us about this relationship over time?
The evidence is very strong. Ice cores, sediment layers, other geological records show a remarkably tight correlation between past concentrations of co-ero and methane and global average temperatures. When greenhouse gas levels were high, temperatures were generally high, and vice versa.
So this isn't just a recent phenomenon.
Oh no, these levels have fluctuated naturally over millions of years due to things like volcanic activity, changes in Earth's orbit, the evolution of plant life. But the rate and magnitude of the increase, especially in co-ero over the last 2 centuries since the Industrial Revolution, is unprecedented in the recent geological record. These rapid human-caused emissions have significantly shifted that natural balance, leading to the warming trends we observe today. The connection is very clear in the paleoclimate data.
Okay, shifting gears dramatically now, from the atmosphere down deep into the Earth. Let's talk plate tectonics, Earth's grand movement. What's actually making these massive continents drift around? What's the engine?
The fundamental driving force is heat from the Earth's interior escaping outwards. This heat drives convection currents within the mantle, the thick layer beneath the Earth's crust.
Convection currents, like in a boiling pot.
Exactly like that, but on a planetary scale and incredibly slow. Hotter, less dense material from deep in the mantle rises, cools as it nears the surface, becomes denser, and then sinks back down.
Good.
This slow circular motion exerts a drag on the rigid lithospheric plates above. The lithosphere, which includes the crust and the very top, a rigid part of the mantle, is broken into these plates.
And they float on something more fluid underneath.
Yes, they effectively float on the asthenosphere, a hotter, more ductile layer of the upper mantle that can flow very slowly over geological time. So the convection currents pull and push these plates around like giant rafts on that slowly churning mantle stew.
Fascinating. So what happens when these rafts collide? The document asks specifically about a convergent plate boundary scenario, where an oceanic plate meets a continental plate.
Right. This is a classic and very active type of boundary. You have a thin but dense oceanic plate, made mostly basalt, colliding with a thicker but less dense continental plate, typically rich in granite.
Density is key here, then.
Absolutely. Because the oceanic plate is denser, when they collide, it's forced to bend and sink down beneath the lighter continental plate. This process is called subduction.
Subduction. Okay, and what does that look like on the surface? What are the results?
Subduction creates some dramatic geological features. First, you get deep ocean trenches right at the boundary, marking where the oceanic plate starts its descent. Think of the Mariana Trench.
The deepest parts of the ocean.
Exactly. Second, as the subducting plate dives deeper, it heats up, releases water, and causes the overlying mantle wedge to melt. This molten rock, or magma, rises to the surface, fueling volcanic mountain chains along the edge of the continental plate. The Andes in South America, the Cascades in the Pacific Northwest, classic examples.
Volcanoes make sense, and I assume all this grinding and sinking causes earthquakes.
Immense seismic activity. Subduction zones are responsible for some of the largest and most destructive earthquakes on the planet, as huge amounts of stress build up and release along the boundary. It's a constant reminder of just how dynamic our planet's surface really is.
All right, we've covered some fundamental forces. Now let's get into the resources themselves, Earth's bounty. Starting with question 8 from our document, the geological genesis of crude oil. Where does oil actually come from? Forget the dinosaur myths.
Right, the dinosaur thing is mostly myth. Crude oil's organic matter origin lies primarily with tiny marine microorganisms, specifically plankton and algae. Think microscopic life in ancient oceans.
Okay, so tiny sea creatures. What needs to happen to them to eventually become oil?
First, you need accumulation and preservation. When these organisms die, they sink to the seafloor and mix with fine sediments like mud and clay. The absolute key here is they must be buried quickly in an environment with very little or no oxygen, an anoxic environment.
Why is the lack of oxygen so critical?
Because oxygen fuels decomposition. Without oxygen, the organic matter doesn't rot away completely. Instead, it gets preserved and starts transforming into a waxy substance called kerogen, mixed within the source rock.
Okay, so step 1, die, sink, get buried without oxygen, become kerogen. What's next?
Next comes a transformation by heat and pressure. Over millions of years, as more sediment piles on top, the source rock gets buried deeper and deeper.
Right.
This increases both the temperature, due to the Earth's natural geothermal gradient, and the pressure. This cooking process transforms the kerogen into liquid hydrocarbons, crude oil.
Is there a specific recipe for this cooking, like temperature range?
There is. It's called the oil window. This is typically at depths of about 2 to 5 kilometers and temperatures between roughly 60 and 120 degrees Celsius.
What happens if it gets hotter than 120 degrees C?
If it gets much hotter, the oil molecules tend to break down further into smaller, lighter molecules, primarily forming natural gas, mostly methane. It gets overcooked for oil.
Interesting. So the oil forms in this source rock within the oil window. Does it just stay there?
Usually not. Oil is generally lighter than the water filling the pore spaces in rock, so it tends to migrate upwards from the dense source rock into more porous and permeable layers called reservoir rocks. Think of sandstones or limestones with lots of interconnected spaces.
Like an underground sponge.
It's a good analogy, but for it to accumulate in large quantities, it needs to be stopped from reaching the surface. It needs to be trapped.
How does it get trapped?
By encountering an impermeable layer of rock, like shale or salt, that acts as a seal or cap rock. This overlying seal, combined with a specific geological structure, like an upward fold called an anticline, a fault block, or a salt dome, creates a geological trap where the migrating oil and gas accumulate.
Okay, so source rock, cooking, migration, reservoir rock, trap. That's the sequence.
That's the typical sequence for conventional oil deposits, yes.
And the document also mentions natural seepage. Oil is just leaking out.
Yes, sometimes the traps aren't perfect, or geological activity creates fractures later on, allowing oil to naturally seep towards the surface. The La Brea tar pits in Los Angeles are a famous example of this natural seepage happening over millennia. It really highlights that oil formation is this slow underground baking process, requiring very specific conditions over vast timescales.
That leads nicely into the next question, number 9. Unconventional natural gas hidden reserves. We hear unconventional a lot now. What makes this gas different from the conventional gas that might accumulate with oil?
The main difference lies in the rock it's trapped in. Unconventional natural gas is found in rock formations with very low permeability. This means the gas molecules can't flow easily through the rock's pore spaces to a well bore like they do in conventional reservoirs.
So it's stuck tight. Needs some extra help to get out.
Exactly. It requires special technologies to extract economically.
What are the main types of this unconventional gas?
Well, probably the most talked about is shale gas. This gas is trapped within the microscopic pores of fine-grained shale rock, which is often also the source rock where the organic matter originally generated the gas.
And how do we get it out of shale?
Recovery requires hydraulic fracturing, or fracking, often combined with horizontal drilling to access more of the shale layer. Shale gas has become a huge player in the energy mix, especially in the U.S.
Okay, shale gas is one. What else?
Another major type is tight gas. This is found in low permeability sandstone or limestone formations. Again, the rock pores aren't well connected, so the gas flow is restricted.
Does it also need fracking?
Yes, tight gas recovery typically also relies heavily on fracking to create pathways for the gas to flow. It's a significant contributor to overall natural gas production.
And is there a third main type?
There is coal bed methane, CBM. This gas is actually generated during the process of coal formation itself and gets stored within the coal seam, absorbed onto the surface of the coal particles, and held in fractures called cleats.
How is that extracted? It sounds different.
It is slightly different. To recover CBM, you typically pump water out of the coal seam. Removing the water lowers the pressure, allowing the methane gas to desorb from the coal and flow to the well. This is particularly important in places like Australia, Canada, and parts of the U.S.
So shale gas, tight gas, coal bed methane.
Yeah.
The common thread is the gas is locked in tight rock, and advances in technology, mainly fracking and horizontal drilling, were needed to unlock them.
Precisely. These technologies turned previously uneconomic resources into major sources of energy, impacting everything from electricity generation to heating and industrial processes.
Okay, let's tackle fracking head on then. Question 10. Fracking process benefits and ecological concerns. You mentioned the process involves drilling and injecting fluid. Can you walk us through that a bit more?
Sure. The process usually starts with drilling a vertical well down thousands of feet, maybe 6,000 to 10,000 feet, to reach the target formation, like a shale layer.
Okay, damn.
Then the drill bit is turned to drill horizontally, sometimes for another mile or more, maybe 5,000 feet or even longer, right through that gas-bearing rock layer.
Okay, so a long horizontal reach. Then what?
Then comes the fracturing stage. A specialized high-pressure fluid, mostly water, but containing sand or ceramic beads called proppant, and a small percentage of chemical additives is pumped down the well and into isolated sections of the horizontal portion.
Immense pressure, you said.
Immense pressure. Enough to actually crack the surrounding shale rock, creating a network of tiny fissures or fractures extending out from the wellbore.
And the sand? What's its role?
The sand, or proppant, is crucial. When the pumping stops and the pressure drops, the sand gets lodged in those newly created cracks, propping them open. This allows the trapped gas, which was stuck in the rock's tiny pores, to flow through the fracture network into the well and up to the surface.
So the fracking creates the highway, and the sand keeps the highway open for the gas. Why is this geologically necessary for these types of rocks?
It goes back to that low permeability shale, tight sandstone, tight limestone. The pores in these rocks are incredibly small and poorly connected. Natural gas simply can't flow through them at economic rates. Fracturing is essential to create those artificial pathways, that permeability.
Makes sense. Now, what about the benefits? Why did this technology take off so dramatically?
There were several key perceived benefits. It dramatically increased access to vast domestic natural gas reserves in countries like the U.S., which reduced reliance on imported energy.
Energy independence, a big driver.
A huge driver. It also helped reduce reliance on coal for electricity generation in many places. Since natural gas burns cleaner than coal in terms of CO2 and air pollutants, this was seen as an environmental benefit in that specific comparison.
Yeah.
And undeniably, it spurred significant economic growth in certain regions, creating jobs related to drilling, production, and associated industries.
All right, those are the benefits. But the concerns are significant too. The document asks for two specific ecological problems.
Yes, and two major ones stand out. First, the potential for groundwater contamination. This is a serious concern. If the well casing isn't properly constructed or fails, or if there are surface spills of fracking fluids or the wastewater produced, those chemicals could potentially leak into underground aquifers used for drinking water.
The chemicals in the fluid are the worry there.
They are. The exact composition varies, but some can be hazardous. The second major concern is induced seismicity, meaning earthquakes caused by human activity.
Fracking itself causes earthquakes.
Not usually the fracking process directly causing large quakes, though it can cause microseismicity. The bigger link is to the disposal of the wastewater that flows back out of the wells after fracking. Injecting huge volumes of this wastewater deep underground into disposal wells has been strongly linked to triggering swarms of small to moderate earthquakes in some areas by increasing fluid pressure on existing faults.
So it's more the disposal of the waste fluid afterwards.
That seems to be the primary driver for the felt earthquakes, yes. Fracking is really a technology with a complex balance sheet unlocking resources, but also presenting genuine environmental risks that need careful management and regulation.
Okay, moving from extracting resources to finding them in the first place, question 15 is about The phases of exploration geology. It sounds like a systematic process, not just luck.
Absolutely. It's a very methodical, cost-tiered approach. You start broad and cheap, and only proceed to more expensive steps if the results from the previous phase are encouraging. It's all about managing risk and investment.
So what's phase one, the cheapest starting point?
Phase one is area selection. This is mostly desk research. Geologists use existing geological maps, satellite imagery, historical mining records, scientific literature, and geological models to identify broad regions, maybe hundreds or thousands of square kilometers, that have the potential to host the type of deposit they're looking for.
Just identifying promising zip codes, essentially.
Kind of, yes, based on the known geological setting.
What's phase two, then? Narrowing it down.
Exactly. Phase two involves remote sensing and mapping. This uses tools like aerial photography, satellite imagery analyzing different light spectra, and airborne geophysical surveys, measuring magnetism, gravity, conductivity, to get a better picture of the surface and subsurface geology without actually being on the ground everywhere.
Looking for clues from afar.
Right. Looking for surface alterations, structures, anomalies that might hint at mineralization. Detailed geological mapping of outcrops also happens here, building a picture of the rock types and structures present. It helps pinpoint smaller target areas for the next phase.
Which brings us to phase three, getting boots on the ground.
Yes, phase three is fieldwork and sampling. This is where it gets more hands-on and moderately expensive. Geological teams go to the prioritized areas and conduct detailed mapping, collect physical samples of rocks, soil, stream sediments, even vegetation.
Why stream sediments?
Streams act like natural samplers, carrying material eroded from upstream. Analyzing stream sediments can give you clues about mineralization further up the drainage basin. These samples are sent to labs for geochemical analysis, looking for trace amounts of the target metals or indicator elements.
Okay, so field evidence and chemical hints. What's the final, most expensive phase if things still look promising?
That's phase four, drilling. This is the make-or-break phase, and by far the most expensive. You bring in drill rigs to bore holes deep into the ground and extract core sample cylinders of rock from depth.
Getting a direct look underneath.
Exactly. Drilling provides direct, physical proof of what's down there, the type of rock, the presence and grade concentration of minerals, the thickness and depth of the deposit. It's essential for confirming a discovery and determining if it's potentially economic to mine. It's like a chef sourcing a rare ingredient. First, research cookbooks, then check online suppliers, then visit a specialty market to sample, and finally, commit to buying a large, expensive batch after thorough testing.
Okay, so drilling confirms the deposit. Now you have ore mixed with waste rock. Question 17 asks about mineral separation from mine to concentrate. How do you separate the valuable stuff?
Right. After mining, you have ore, which contains valuable minerals mixed with unwanted rock called gangue or tailings. The goal of mineral processing or beneficiation is to concentrate the valuable minerals. This usually starts by crushing and grinding the ore into fine particles to liberate the mineral grains.
Breaking it down so the minerals are physically separate.
Precisely. Then you use methods that exploit differences in their physical or chemical properties.
Like what? What's a common method based on physics?
A classic one is Method 1, gravity separation. This works well when the valuable mineral is much denser, much heavier than the waste rock.
Like gold.
Exactly like gold. You mix the crushed ore with water and use shaking tables, spirals, or sluices. The heavy gold particles settle out quickly while the lighter waste material gets washed away. It's also used for other heavy minerals like tin ores.
Simple, but effective for heavy stuff. What if the density difference isn't that great?
Then you might use Method 2, flotation, specifically froth flotation. This is incredibly widely used, especially for sulfide ores like copper, lead, and zinc.
How does flotation work? Sounds like magic.
It's clever chemistry.
Yeah.
You mix the finely ground ore with water and specific chemicals called collectors and frothers. Air is bubbled through the mixture. The collectors make the target mineral particles water repellent, hydrophobic, so they attach to the air bubbles.
Ah, they stick to the bubbles.
Right. The bubbles rise to the surface, forming a mineral-rich froth, which is then skimmed off. The waste rock doesn't attach to the bubbles and sinks.
Very clever. What about magnetic minerals?
For those, you use Method 3, magnetic separation. If your ore contains a magnetic mineral, like iron ores such as magnetite, you can simply pass the crushed ore over powerful magnets.
And the magnetic stuff sticks.
The magnetic minerals are attracted and separated, while the non-magnetic waste passes through. Simple and efficient for the right type of ore.
Okay, one more. What about chemical methods?
Method 4, leaching. This involves using a chemical solution to selectively dissolve the target metal from the ore. For example, a dilute cyanide solution is commonly used to dissolve gold from its ore. Heap leaching. Acid solutions are used to leach uranium or some copper oxides. Once the metal is dissolved in the solution, the leachate, it's recovered through further chemical processes.
So gravity, flotation, magnets, or chemicals, using the specific properties of the mineral to isolate it, like sorting different ingredients using a sieve, a skimmer, a magnet, or dissolving one selectively.
That's a great way to put it. Each method is tailored to the specific characteristics of the ore being processed.
Now, let's step back again. How did these concentrations of metals even happen naturally? Question 18 talks about geological recipes for metal concentration. Nature must have ways to bring these elements together.
It absolutely does. These natural concentration processes are essential because most metals are actually very dispersed in the Earth's crust. Or deposits form where geological processes have concentrated them, often by thousands of times, making extraction feasible.
So what's one major geological recipe?
Process 1, magmatic processes. This happens deep underground related to molten rock or magma. As a large body of magma cools and solidifies, certain minerals crystallize at different temperatures. Sometimes, dense, early crystallizing minerals containing valuable metals can settle out and accumulate at the bottom of the magma chamber.
Gravity again, but within the magma.
Yes, it's called gravity segregation or magmatic segregation. This is important for concentrating metals like chromium, nickel, and platinum group elements, often found in large, layered intrusions of mafic or ultramafic rock. The Sudbury Basin in Canada, famous for nickel, is linked to a massive magmatic event, albeit triggered by an impact.
Okay, settling out of magma. What's another major way?
Process 2, hydrothermal processes. This is incredibly important for many metals. It involves hot, watery fluids circulating through rocks in the Earth's crust.
Hot water carrying metals.
Exactly. These fluids, often heated by nearby magma bodies or deep circulation, can dissolve metals from the rocks they pass through or carry metals released from the magma itself. As these fluids move into cooler or chemically different environments or experience pressure drops, they precipitate the dissolved metals, depositing them in veins, fractures, or porous rocks.
What kinds of metals are formed this way?
A huge variety. Many copper deposits, like porphyry coppers, gold, silver, lead, zinc, and others formed from hydrothermal fluids. Think of hot springs depositing minerals, but happening underground on a massive scale over long periods.
Fascinating. And the third main process type, something happening more at the surface.
Process 3, sedimentary processes. These processes concentrate metals at or near the Earth's surface, often involving water. One way is through chemical precipitation. For example, vast iron deposits called banded iron formations formed in ancient oceans when dissolved iron precipitated out chemically. Bauxite, the ore for aluminum, forms from intense weathering of rocks in tropical climates, concentrating aluminum oxides.
And you mentioned placer deposits earlier.
Yes, that's another type of sedimentary process mechanical concentration. Weathering releases dense, durable minerals like gold or diamonds from their source rock, and flowing water concentrates them in placer deposits. Even lithium, which we'll discuss more, gets concentrated in brines through evaporation in closed basins, another sedimentary process. So nature uses heat, pressure, fluids, water, and weathering as its tools in these geological recipes.
Let's focus on one of those sedimentary examples. Question 20. Gold placer deposits nature's sorting system. Why does gold end up concentrated in rivers and streams so often?
It comes down to two really key mineral characteristics of gold. First, it's incredibly high density. Gold is extremely heavy, about 19.3 times denser than water.
19 times, wow.
Yeah. So when gold particles are eroded from their source rock and carried by water, even a slight decrease in the water's velocity causes the heavy gold to drop out and settle, while lighter sand and gravel get carried further downstream. It naturally accumulates in low-energy spots like river bends, behind boulders, and crevices in the bedrock.
Nature's sluice box.
Pretty much. The second key characteristic is its chemical stability. Gold is very inert, meaning it's highly resistant to corrosion and chemical weathering.
It doesn't rust or dissolve easily.
Exactly. While other minerals might break down or dissolve over time as they tumble downstream, gold persists in its metallic form. This allows it to survive the journey and accumulate in these placer deposits over long periods.
So it's heavy enough to get sorted by water flow and tough enough to survive the process.
That's the perfect summary. This natural sorting process is what created the easily accessible alluvial gold deposits that sparked so many historical gold rushes. The miners were essentially collecting gold that nature had already conveniently concentrated for them.
From shiny gold to another famously hard mineral. Question 24. Industrial diamonds, the unsung workhorses. Most diamonds mined aren't for jewelry, are they?
That's absolutely right. Somewhere between 80 and 90% of all natural diamonds mined are classified as industrial grade, not gem quality. They might be too small, oddly shaped, poorly colored, or have too many internal flaws for use in jewelry.
But they're still incredibly useful. What makes them so valuable for industry? The document asks for two key characteristics.
The first and most famous is their extreme hardness. Diamond is the hardest known natural substance, a 10 on the Mohs hardness scale. Nothing else natural comes close.
So they can cut or grind anything.
Pretty much anything. This makes them indispensable as abrasives and in cutting and drilling tools. They're used to cut concrete, rock, metals, glass, anything hard. Diamond-tipped drill bits, saws, grinding wheels are essential in construction, manufacturing, mining.
Okay, extreme hardness. What's the second key property?
The second is their exceptionally high thermal conductivity. This might be less intuitive, but it's crucial. Diamonds conduct heat better than almost any other material, even better than copper or silver.
Why is that useful industrially?
In applications like high-speed drilling or grinding, a lot of heat is generated by friction. A diamond tool can quickly draw that heat away from the cutting edge, preventing the tool from overheating, warping, or failing. It keeps the tool cool and functional. This property is also used in electronics, in heat sinks, to cool down powerful microchips.
So they cut the hardest materials and stay cool while doing it.
Exactly. These two properties make industrial diamonds incredibly valuable workhorses, far more vital to modern technology and manufacturing than gem diamonds are to jewelry. They really are unsung heroes. And just a reminder, they form deep in the mantle under immense pressure, not from coal. That's a persistent myth.
Sticking with gems, but moving to the pretty ones. Question 25 discusses the allure of gemstone impurities. It's amazing that tiny flaws or additions are what give gems their color and value.
It really is counterintuitive, isn't it? But for many colored gemstones, their beauty and value depend almost entirely on trace impurities, tiny amounts of elements that aren't part of the mineral's basic chemical formula, but get incorporated into the crystal structure as it grows.
So the base mineral might be common, but the impurity makes it special. Can you give us 5 examples, excluding diamond?
Sure. Let's start with ruby. Its stunning deep red color comes from the base mineral corundum, which is aluminum oxide, haluro. The impurity responsible for the red is chromium Cr, substituting for some aluminum atoms.
Okay, ruby is corundum plus chromium. What about sapphire?
Sapphire is also corundum. Its classic blue color is typically caused by trace amounts of iron, At, and titanium Ti working together within the crystal lattice. Other impurities can make sapphires yellow, pink, green.
Same base mineral, different impurities, different gem. Got it. How about emerald?
Emerald is the vibrant green variety of the mineral beryl, which has a more complex formula, Bal-Zero. The green color comes from impurities of chromium and sometimes vanadium.
Okay, beryl plus chromium vanadium is emerald. Is aquamarine related?
Yes, aquamarine is also beryl. Its lovely light blue to blue-green color is caused by impurities of iron, specifically the FeO iron.
So different state of iron than in blue sapphire, presumably.
Exactly. And one more. Let's do amethyst. This is the purple variety of quartz, FiO, a very common mineral. The purple color is caused by trace amounts of iron, FeO impurities, combined with exposure to natural radiation over geological time, which creates color centers in the crystal.
Wow, so tiny chemical differences, sometimes triggered by radiation, turn common minerals like corundum, beryl, and quartz into precious gems.
Precisely. It's a fantastic example of how subtle variations in geochemistry create immense beauty and value.
Let's talk about a metal that's crucial for batteries, lithium. Question 26 points out it's classified as an evaporate resource, which sounds weird for a metal. How does that work?
It does sound odd at first, but it makes sense when you look at how lithium often concentrates geologically. While lithium can be mined from hard rock minerals like spodumene, a huge portion of the world's lithium resources are found dissolved in salty brines, similar to how table salt accumulates.
So it's dissolved in water.
Yes, in very salty water found in specific geological settings called evaporate basins. These are typically arid regions with closed basins, meaning water flows in but not out except through evaporation.
Like a desert salt flat.
Exactly. Over long periods, water flowing into the basin dissolves tiny amounts of lithium from surrounding rocks. As the water evaporates under the intense sun, the dissolved salts, including lithium salts, become highly concentrated in the remaining brine, often trapped underground beneath the salt crust. The lithium triangle in South America, Chile, Argentina, Bolivia, is famous for these lithium-rich brine deposits beneath vast salt flats.
And how is it extracted from these brines?
The extraction method reinforces the evaporate classification. The brine is pumped up from underground into huge, shallow evaporation ponds. The sun does the work, evaporating the water over many months.
Leaving the salts behind.
Right. As the water evaporates, the concentration of lithium salts increases significantly. Different salts precipitate out at different stages, allowing for the eventual separation and processing of lithium carbonate or lithium hydroxide, the compounds used in batteries.
So because it concentrates through evaporation and is extracted using evaporation ponds, it's classified with other evaporate minerals like salt or gypsum, even though it's a metal.
Precisely. It's a classification based on its geological occurrence and extraction method. It's like making rock candy evaporation concentrates the dissolved sugar, lithium salts, from the brine. And this method is currently more cost-effective than hard rock mining for much of the world's lithium supply.
Okay, one last one in this section. Question 21. Base versus ferroalloy metals core distinctions. What separates these two groups?
They're distinguished mainly by their primary use and properties. Base metals are generally the common, non-precious metals that are not iron and are used for their own inherent properties.
Okay, what kind of properties and examples?
They're often valued for things like conductivity, electrical and thermal, corrosion resistance, or malleability. Think of copper. Crowd, used everywhere in wiring because it conducts electricity so well. Or zinc, Zn, used to galvanize steel to prevent rusting. Lead, Pb, used in batteries and shielding due to its density and chemical properties. They're used in bulk for what they are.
Got it. So what are ferroalloy metals then? The name gives a clue.
Exactly. Ferro relates to iron. Ferroalloy metals are metals that are primarily used as additives to iron to make steel alloys. They're added, often in small percentages, specifically to enhance or modify the properties of steel.
So they're not used on their own, but to improve steel.
Largely, yes.
Yeah.
Their purpose is to give steel specific characteristics like increased strength, hardness, toughness, or resistance to corrosion or heat.
Examples.
Key examples include chromium, Cr, which is essential for making stainless steel resistant to rust. Manganese, An, adds toughness and wear resistance to steel. Vanadium V significantly increases steel's strength and durability used in tools, axles, and structural components. Molybdenum, nickel, tungsten are others.
So base metals are the workhorses used for their own properties, while ferroalloys are like the vitamins or spices added to steel to make it perform better for specific jobs.
That's a perfect analogy. Base metals are the main ingredients. Ferroalloys are the critical performance enhancers for iron's main product, steel.
All right, we've covered a lot of ground, literally, from deep earth processes to metals. Now let's shift focus to the human dimension. Question 5 uses population pyramids, Uganda versus Norway, as a case study. These diagrams really paint a picture, don't they?
They absolutely do. A population pyramid is a fantastic visual tool. It shows the distribution of different age groups in a population, typically for a specific country or region, and it's split by gender.
And the shapes tell a story about development. What does Uganda's pyramid look like?
Uganda, as a representative developing country, has a classic pyramid shape. Very wide at the base, representing a large number of young children, and then it narrows very quickly as you go up in age groups. It's bottom-heavy.
Why that shape? Lots of kids, fewer older people?
Primarily due to high birth rates combined with relatively high death rates, particularly high childhood mortality. Factors like limited access to healthcare, less effective sanitation, poverty, and disease contribute to fewer people surviving into older age groups.
So the implication for child survival is quite stark.
Yes, it visually shows that while many children are born, a significantly smaller proportion survive to reach adulthood compared to more developed nations.
And how does Norway, as a developed country, contrast? What's its pyramid shape?
Norway's pyramid looks very distant. It's much more rectangular or column-shaped. The base is narrower, reflecting lower birth rates, and it stays relatively wide much further up, indicating that a large proportion of the population survives into old age. Sometimes the base might even be slightly narrower than the middle sections.
Why the difference? Low birth rates
And low death rates across all age groups, especially low infant and child mortality. This is due to excellent healthcare, good nutrition, high living standards, and consequently, high life expectancy.
So in Norway, fewer kids are born, but most of them make it to old age.
Precisely. The contrast highlights the profound impact of economic development, healthcare, and education on a nation's demographic structure and survival patterns. It's like Uganda is rapidly stacking many small blocks that quickly taper off, while Norway is stacking more consistently sized blocks much higher.
That leads directly into question 6, population growth and resource strain. It's obvious more people use more resources, but the document asks for 2 distinct ways this strain happens.
Right. It's helpful to break it down. The first major way is pretty direct. Increased demand for essential resources like food and water.
More mouths to feed, more water needed to grow the food.
Exactly. As population grows, you simply need more food production, and agriculture is incredibly water intensive. In many lower and middle income countries, something like 80% or more of their freshwater withdrawal goes just to farming.
80%.
Yeah. So population growth directly translates to needing more farmland, more irrigation, more fertilizers, all of which puts immense strain on water sources like rivers and aquifers, and on ecosystems. Think about expanding agriculture in places like India or sub-Saharan Africa. It often comes with significant water stress.
Okay, food and water is number 1. What's the second distinct way population growth strains resources?
The second way is through increased energy use and the demand for materials for infrastructure development.
More people need more power, more houses, more roads.
Precisely. Especially as populations become more urbanized and achieve higher living standards, energy demand for homes, industry, and transportation surges. You also need vast amounts of materials: cement, steel, copper, aggregates to build the houses, schools, hospitals, roads, and power plants required.
Can you give an example of that energy infrastructure demand?
Think of the explosive growth of cities in many developing nations, like Lagos or Jakarta. Energy consumption skyrockets, vehicle use increases, construction booms. One study noted a 53% jump in energy use in developing countries over less than a decade in the early 2000s. And while population growth is highest in developing nations, consumption per person is vastly higher in wealthy nations. The richest billion people consume about half the world's energy. So more people globally, particularly striving for higher living standards, inevitably means more mining, more fossil fuel burning, historically, more deforestation for materials or land, and generally greater resource depletion and pollution. It's like a growing household needing more groceries and water, but also bigger appliances, more cars, and maybe an extension built onto the house.
Understanding that growth leads us to question 7, the seasons of demographic transition. This sounds like a model for how population patterns change over time.
It is. The demographic transition model describes a typical sequence of changes in birth and death rates as a country develops economically and socially. It's usually broken down into 4 main stages, like seasons.
What's stage 1, the starting point?
Stage 1 is pre-industrial. In this stage, both birth rates and death rates are high. Death rates fluctuate with famine and disease, but overall, population growth is very slow or stable. Think pre-modern societies with poor healthcare and sanitation, high infant mortality, and where large families might be needed for agricultural labor.
Okay, high births, high deaths, stable population. What happens in stage 2?
Stage 2 is transitional. This is where the changes begin. Death rates start to fall dramatically due to improvements in public health, sanitation, food supply, and basic medicine. However, birth rates remain high because social norms around family size take longer to change.
So deaths drop, but births stay high,
leading to rapid population growth. This is the stage many developing countries went through in the 20th century or are still in.
Then comes stage 3. Do birth rates start to fall then?
Yes. Stage 3 is the industrial stage. Now, birth rates begin to decline significantly. This is driven by factors like increased urbanization, children less economically useful, rising education levels, especially for women, better access to contraception, and lower infant mortality rates, meaning families don't need to have as many children to ensure some survive. Population growth starts to slow down.
Okay, births falling towards the already low death rates. What's the final stage?
Stage 4 is post-industrial. In this stage, both birth rates and death rates are low. Population growth becomes stable again or may even start to decline if birth rates fall below the replacement level, roughly 2.1 children per woman. Many developed countries in Europe, North America, and East Asia are considered to be in this stage.
So what's the main engine driving a country through these stages, these seasons?
The primary factor is economic development and the social changes that come with it. Improvements in healthcare, education, especially female education, living standards, and access to family planning are the key drivers that push countries from high birth-death rates to low birth-death rates. It's a remarkably consistent pattern globally, though the speed can vary. It's like a country moving through economic seasons from a harsh demographic winter to a more balanced autumn.
Let's zoom in on a specific interaction between industry and society. Question 16 is about building social capital in mining ventures. Why is this social capital so important for, say, a mining company?
It's incredibly important, arguably as crucial as the financial capital or the geological resource itself. Building social capital essentially means building trust, strong relationships, and goodwill with the local community where the mine operates or plans to operate.
Why is that trust so vital? Can't they just get permits and start digging?
Technically, maybe, but practically, it's a recipe for disaster. Mining is inherently disruptive. It impacts land, water, local economies, traditional ways of life. Without community trust and support, what's often called a social license to operate, companies face constant conflict, protests, legal challenges, costly delays, and sometimes projects get shut down entirely. Ignoring the community is a massive risk.
Okay, so it's essential for smooth operations and long-term viability. How does a company actually build this social capital? The document asks for 3 ways.
Right. First, genuine community engagement. This means more than just holding one token meeting. It involves ongoing, open, two-way communication, actively listening to concerns, transparently sharing plans and potential impacts, good and bad, and involving the community in decision-making where possible. It fosters mutual understanding and respect.
Makes sense. Listen and involve. What's another way?
Second, providing tangible local hiring and investment. Prioritizing hiring local residents for jobs, offering skills training, sourcing supplies locally, these create direct economic benefits that the community can see and feel. Investing in local infrastructure like schools, clinics, or roads also demonstrates a commitment beyond just extracting resources.
Sharing the economic benefits directly. And the third way, probably related to the environment.
Absolutely. Third is environmental transparency and responsibility. Companies need to be upfront and clear about potential environmental impacts and, more importantly, about their detailed plans to mitigate those impacts, protecting water quality, managing dust, reclaiming land after mining. Demonstrating a strong commitment to environmental stewardship and backing it up with action builds crucial confidence. Social capital isn't just nice to have, it's fundamental risk management and ethical practice for resource development today.
Let's talk building materials. Question 22 focuses on dimension stone from structure to adornment. What exactly is dimension stone?
Dimension stone is natural rock like granite, marble, limestone, sandstone that's been quarried and then cut or shaped into specific sizes or shapes like blocks, slabs, or tiles. It's distinct from crushed stone or aggregate.
And historically, it was used for, everything structural, right?
For much of human history, yes. It was valued for its durability, strength, and beauty, and used extensively in structural roles. Think pyramids, temples, cathedrals, castles, bridges. The main load-bearing components were often made of carefully cut stone.
But that's changed. We don't build skyscrapers out of granite blocks anymore.
Right. Its use in purely structural roles has significantly declined over time.
Why the shift away from using it structurally?
Primarily because of cost and labor intensity. Quarrying large blocks, transporting them, and meticulously shaping and fitting them is very expensive and time-consuming compared to modern alternatives like reinforced concrete and structural steel. These materials can be produced and erected much more quickly and cheaply, especially for large structures.
So where is most dimension stone used today, and where is it produced?
Today, dimension stone is used much more for decorative purposes, building facades, cladding, flooring, countertops, paving stones, monuments, sculptures. It's valued more for its aesthetic appeal than its structural necessity. Production is concentrated in countries with favorable geology and often lower labor costs, with China, India, Turkey, and Italy being major global producers. It's transitioned from being the structural staple to more of a decorative, high-value finish like a gourmet ingredient rather than the main course.
Speaking of modern materials, question 23 takes us from limestone to concrete, a transformative journey. How do we get from that rock, limestone, to the concrete we see everywhere?
It's a fascinating industrial process, really a chemical transformation. It starts, as you say, with step one, limestone acquisition and crushing. Limestone, calcium carbonate, capoate, is the primary raw material. It's quarried and then crushed into smaller, relatively uniform pieces. Clay or shale is also added.
Okay, crushed rock. What's the key transformation step?
Step two, calcination and clinker formation. This is the heart of the process. The crushed limestone and clay mixture is fed into a huge rotating kiln and heated to extremely high temperatures, around 1450 degrees Celsius.
That's incredibly hot.
It is. This intense heat causes a chemical reaction called calcination. The limestone decomposes, releasing carbon dioxide, and the components recombine to form new compounds, primarily calcium silicates. These marble-sized gray lumps that come out of the kiln are called clinker.
Clinker, so that's not cement yet.
Not yet. Step three is cement production. The cooled clinker is then ground into a very, very fine powder in large mills. A small amount of gypsum, calcium sulfate, is added during grinding. This fine powder is Portland cement, the key binding agent.
Why add gypsum?
Gypsum acts as a retarder. It controls how quickly the cement sets or hardens when mixed with water. Without it, it would set almost instantly.
Right, need time to work with it. And the final step.
Step four, concrete mixing. To make concrete, you simply mix the Portland cement with water, sand, fine aggregate, and gravel or crushed stone, coarse aggregate. The water reacts chemically with the cement in a process called hydration. This reaction forms crystals that interlock and bind the aggregates together into a hard, durable, rock-like mass.
So limestone gets cooked into clinker, clinker gets ground with gypsum to cement, and cement gets mixed with water and aggregates to make concrete, like baking a very durable cake from rocks.
That's a great analogy. And the result is the most widely used synthetic material on Earth, fundamental to modern construction.
Another crucial modern material is aluminum. Question 19 focuses on aluminum production energy demands and recycling efficiency. What's the biggest headache when making aluminum from its ore? Bauxite.
The single largest problem is the incredibly high energy consumption. Producing primary aluminum from bauxite ore is one of the most energy-intensive industrial processes known.
Why so much energy?
It's a two-step process. First, the Bayer process refines bauxite ore into pure aluminum oxide, or alumina. Then, the Hall-Héroult process uses electrolysis, passing a massive electric current through molten alumina dissolved in cryolite to break the extremely strong chemical bonds between aluminum and oxygen. This electrolysis step requires enormous amounts of electricity.
Okay, massive electricity needs. How does that compare to using recycled aluminum?
The comparison is staggering. Producing aluminum from recycled cans and scrap uses about 95% less energy than making it from virgin bauxite ore.
95% less. That's huge.
It's a massive difference. And consequently, it also generates about 95% fewer greenhouse gas emissions.
Why is recycling so much more efficient?
Because recycling essentially just involves melting the aluminum scrap down and recasting it. You completely skip the energy-intensive mining, transportation, refining, Bayer process, and especially the electrolytic reduction Hall-Héroult process steps. You're just remelting the finished metal.
So the benefits are enormous, both economically and environmentally.
Absolutely. It's why aluminum is often called one of the most recyclable materials we have. Making primary aluminum is like cooking a complex meal entirely from scratch, requiring huge amounts of energy. Recycling aluminum is like simply reheating the leftovers much, much quicker and less energy intensive.
Let's turn back to fossil fuels for a moment, specifically coal. Question 11 covers coal varieties, carbon content, and energy production. I know there are different types, like lignite and anthracite. How do they differ?
The different types, or ranks, of coal represent stages in a long geological process where plant matter, peat, is buried, compressed, and heated over millions of years. The core concept is that as you go up in rank, the carbon content increases, moisture decreases, and the energy released per kilogram gets higher.
So deeper burial and more heat means better coal.
Essentially, yes, it's a process of maturation.
What are the main types, starting from the lowest rank?
Okay, lowest energy, technically pre-coal, is peat. Partially decayed plants, high moisture, maybe 50–60% carbon, low energy value, maybe 5–7 megajoules per kilogram, MJ/kg.
They're the first true coal.
Lignite. This is the youngest, softest coal, forms at relatively shallow depths, maybe up to 1,500 meters, temps up to 50 degrees C. Carbon content is higher, 60–70%. Energy around 10–20 MJ/kiln, still quite moist.
What's next up the ladder?
Subbituminous coal. Carbon content around 70–76%, energy 1824 mJ kilogram. It's a major fuel source for electricity generation in some places.
And the most common type used globally.
That would generally be bituminous coal. Forms deeper, 1,000 to 5,000 meters, temps up to 150 degrees Celsius. Carbon content is significantly higher, 77–87%. Energy content, 24–35 mJ kilogram. This is the workhorse coal for power plants and also used to make coke for steel production.
And the highest rank, the best quality.
Anthracite. This forms under the greatest heat and pressure, beyond 5,000 meters depth, over 150 degrees C. It has the highest carbon content, 86–97%, and the highest energy density, typically over 30–35 mJ kilograms. It's hard, shiny, burns very hot and cleanly with little smoke.
So pedal lignite, bituminous anthracite. Each step squeezing out more water and volatiles, concentrating the carbon and energy, like compressing that wet sponge.
Exactly. More geological processing yields higher energy density.
Moving from coal to nuclear. Question 12 is about uranium enrichment for nuclear fuel and weapons. Why do you need to enrich uranium? Can't you just use it as it comes out of the ground?
Unfortunately, no. The necessity for enrichment comes down to isotopes. Natural uranium mined from the Earth is composed almost entirely of the isotope uranium-238, U-238, about 99.3% of it.
Talk.
The isotope needed to sustain a nuclear chain reaction, the fissile isotope, is uranium-235, U-235. But U-235 makes up only about 0.7% of natural uranium.
Less than 1%, so not enough to keep a reaction going easily.
Exactly. That 0.7% isn't enough to reliably sustain the chain reaction needed in most types of nuclear reactors, or certainly not for a weapon. Enrichment is the process of increasing the percentage of U-235 relative to U-238.
What level of enrichment is needed for typical nuclear power plants?
For most commercial nuclear reactors, the uranium fuel needs to be enriched to about 3% to 5% U-235. This is called low-enriched uranium, LEU. It's enough to sustain a controlled chain reaction for power generation.
Okay, 3–5% for fuel. What about for nuclear weapons?
That requires much, much higher enrichment levels. To create a rapid, uncontrolled chain reaction needed for an explosion, you typically need highly enriched uranium, HEU, which is usually defined as around 90% U-235 or even higher.
Wow, 90% versus 3–5%. A massive difference.
A huge difference, and achieving that high level of enrichment is technologically very challenging and expensive, which is a key factor in nuclear non-proliferation efforts. It's like trying to start a bonfire. Natural uranium is like mostly damp logs, U-238, with just a tiny bit of dry kindling, U-235. Enrichment is the process of concentrating that essential kindling. You need a little extra kindling for a steady campfire reactor fuel, but a whole pile of it for a rapid inferno weapon.
Let's compare two solar technologies now. Question 13 asks us about heliostat plants versus solar PVA comparison. How does a heliostat plant work? It sounds complex.
Heliostat plants, also called concentrated solar power or CSP, are indeed quite complex. They use a large field of computer-controlled mirrors called heliostats. Each mirror tracks the sun and reflects its light, focusing it onto a central receiver mounted on top of a tall tower.
So hundreds or thousands of mirrors all pointing at one spot.
Exactly. This concentrated sunlight creates intense heat at the receiver, which is used to heat up a fluid, often molten salt or a special oil. This superheated fluid then generates steam, which drives a conventional turbine connected to a generator, producing electricity.
Like a traditional power plant, but using concentrated sunlight instead of burning fuel. Can it generate power when the sun isn't shining?
A key advantage is that many CSP plants incorporate thermal storage. They can store the hot fluid, like molten salt, in insulated tanks and use that stored heat to continue generating steam and electricity for several hours after sunset or during cloudy periods. This makes the power dispatchable.
What kind of resources do they need?
They need a lot of land for the mirror field, the mirrors themselves, complex tracking systems, the tower and receiver, which require high-temperature materials, and often large amounts of molten salt for storage. They're best suited for large, utility-scale projects in areas with intense, direct sunlight.
Okay, how does that compare to the familiar solar photovoltaic PV panels on rooftops?
Solar PV is fundamentally different. PV panels use semiconductor materials, usually silicon, that directly convert sunlight into electricity through the photovoltaic effect. When photons from sunlight hit the panel, they knock electrons loose, creating an electric current. No mirrors, no heated fluids, no turbines involved in the conversion itself.
Much simpler mechanically. Can PV generate power after sunset?
Not on its own. Standard PV systems only produce electricity when the sun is shining on them, unless they're coupled with battery storage systems, which adds cost and complexity.
And resources needed for PV.
Primarily the panels themselves, silicon glass, aluminum frames, some trace elements, inverters to change the DC electricity to AC wiring, and mounting structures.
Which one is more common? It feels like PV is everywhere now.
PV is far more common globally. Its simplicity, modularity, you can install one panel or millions, rapidly falling costs, and ease of installation on rooftops or large fields have made it the dominant solar technology. Heliostats are more like sophisticated outdoor ovens with built-in heat storage for large-scale power, while PV is like a direct conversion solar calculator, scalable from tiny to huge.
Finally, let's look at wind power challenges. Question 14 asks about the problems. Wind seems clean, but what are the downsides?
It definitely has challenges. Problem 1 is intermittency. The wind doesn't blow constantly and its speed varies. This means wind power generation is variable and not always available when needed.
Unreliable for consistent power.
It makes it difficult to rely on for base load power without significant backup from other sources like gas plants or large-scale energy storage like batteries, both of which add cost and complexity to the grid. Predicting wind output is also challenging.
Intermittency is a big one. What's another problem?
Problem 2 is noise and visual impact. Modern wind turbines are enormous structures. They can produce a low-frequency whooshing sound that some nearby residents find annoying or disruptive. And visually, large wind farms can significantly alter the landscape, leading to aesthetic objections and IMB,
Right.
not in my backyard, opposition.
Citing them can be controversial.
Very much so. Finding locations with good wind resources that are also acceptable to local communities can be difficult.
And the third problem mentioned in the outline, wildlife.
Yes. Problem 3 is wildlife impact. The large, fast-spinning blades can pose a collision risk to birds and bats, especially if turbines are located along major migration routes or near important habitats. This raises ecological and conservation concerns that need to be addressed through careful siting and sometimes operational adjustments.
So intermittency, local impacts on people, noise visual, and impacts on wildlife.
Those are the main challenges. It highlights that even clean energy sources require careful planning, technological improvements like better forecasting and storage, and thoughtful integration into the environment and society. Wind farms are like powerful athletes relying on variable natural conditions. Their performance fluctuates and their presence impacts the surrounding community and ecosystem. #tag outro.
Wow. We have covered an incredible amount of ground today, truly a deep dive. From the absolute basics of energy units like the joule and the watt, to the composition of our atmosphere and how tiny amounts of greenhouse gases play such a huge role in trapping heat.
Right, that natural greenhouse effect.
And the immense power of plate tectonics driven by convection, constantly reshaping our planet through processes like subduction.
Then we dug into how resources like crude oil actually form that whole journey from marine microorganisms to trapped hydrocarbons.
And the difference between conventional oil and unconventional gas, like shale gas, and the technology fracking used to get it out with all its benefits and significant concerns.
We covered the systematic hunt for resources through exploration geology, those clever mineral separation techniques.
Flotation, magnetic separation.
Yeah. And the amazing geological recipes nature uses to concentrate metals through magmatic, hydrothermal, and sedimentary processes.
We learned why gold ends up in riverbeds, why most diamonds are industrial workhorses, not gems, and how tiny impurities give gemstones like rubies and emeralds their color.
Plus, the surprising story of lithium as an evaporate, the difference between base and ferroalloy metals.
And then shifting to the human side, those population pyramids telling stories about Uganda and Norway, the real strains of population growth on food, water, and energy.
The stages of demographic transition, the absolute necessity of building social capital in mining.
The history of dimension stone, the process of the making concrete from limestone, the energy dilemma of aluminum production versus recycling.
The different ranks of coal, the critical concept of uranium enrichment for fuel versus weapons.
Right.
Comparing large-scale heliostat solar plants to ubiquitous PV panels. And finally, acknowledging the real challenges of wind power, like intermittency and wildlife impacts.
The biggest takeaway for me, really, is just how interconnected everything is. Seemingly disparate topics, the structure of a Euro molecule, the density of gold, the temperature deep underground, population growth rates, they all weave together through Earth's processes and directly impact resource availability in human society.
Exactly. Geology, physics, chemistry, they fundamentally underpin almost everything we use and how our societies function. Understanding these natural recipes and journeys for resources isn't just for passing an exam, it's essential for making informed choices about how we manage our planet.
And it changes how you see the world, doesn't it? When you realize that every object around you, your phone, your house, the road you drive on, has this deep geological story embedded within it. A story: formation, extraction, processing, and impact.
It absolutely does.
Right.
Which leads to a final thought, perhaps. Understanding these connections, the ones we've explored today, is really the key to managing our finite resources more sustainably. As test time approaches for some, but more importantly, as real-world decision-making time impacts all of us.
Mm-hmm.
Keep observing the world with this geological lens. Ask yourself, where did this come from? How was it formed? What are the implications of using it? That curiosity is where real understanding begins.